everyone, welcome back. My name's Rob, and this is a class on an introduction to statistics for the psychological sciences. And this is the second part of a four-part lecture sequence that explores some basic concepts that link statistics with scientific inquiry in general. And so we left off at the last lecture talking about the distinction between inferential statistics and descriptive statistics. We described what inferential statistics were. We're going to go into more detail in this lecture. We'll also talk about a variety of other topics that are of crucial importance, that are kind of the bedrock concepts that you're going to rely upon for the remainder of the semester. So we'll talk about the distinctions between populations and samples, different ways of sampling, errors that are introduced to the inferences that we might make, as well as just common nomenclature like independent variable, dependent variable. We'll talk about some common study designs, as well as, extraneous and confounding variables. But we'll get to all of that. Why don't we just march on along? I'd like to start by just kind of picking up a question that was posed in the first part of this lecture, which was about, do birds of a feather flock together or do opposites attract? And so we kind of examined this question across various different ways people come to knowledge. And I neglected to share with you what the scientific method had shown about this question. And despite the fact that intuitively people might feel one way or another, the scientific method has provided evidence, particularly in the field of social psychology, over the course of the last 40 years, demonstrating over and over and over that, in fact, birds of a feather flock together. Right? We tend to be attracted to people who are similar to us, not to people who are opposite or different from us. I'd be happy to go into that research, but I am mindful of your time. So let's just start where we left off in the last part of this lecture. So we have two main buckets that statistics fall into. We've got descriptive statistics. We've got inferential statistics. So descriptive statistics are used to describe the data of a sample of people. So, for example, I could hypothesize that men tend to prefer dogs over cats, and that women tend to prefer cats over dogs. And I go out and I ask 20 men and I ask 20 women whether they would prefer a dog or a cat. I might ask them using a survey or something like that. And then we aggregate their responses. And if this is what we found, we could say, okay, 60% of the men surveyed preferred dogs, and 70% of the women surveyed preferred cats. And the key here is this is a descriptive statistic of the sample that we assessed. Now, it doesn't have to be percent. It could be a mean, a standard deviation. It could be a variety. It could take a variety of different forms. But the central feature of descriptive statistics is that they're used to describe sample data. Now, this is in contrast to inferential statistics. So inferential statistics, the purpose of inferential statistics is to use data from a sample of the, for example, the men and the women that we collected the data for, right? To make an inference about the populations they represent, right? So here we go. Here is a example of a population and a sample. So a population is a well-defined specific group of people, right? And a sample is a subset of the population. It is a group of individuals that are taken from the population to represent the population. And so the reason we would do this is, frankly, we don't have access to the whole population. So, for example, say you wanted to study whether or not some variable influences depression. Well, the question you really want to ask isn't, does it influence the people that I measured in my study who have depression? The question is, does it influence people with depression? In the same way, you could say, like if you did some kind of like election poll, you're not so much interested in the people that you polled, right? You're interested in the general population that those people represent. You're not interested in how a random group of people vote. You're interested in how the entire state or entire country votes, right? And so a population represents, you can think of it as everyone, right? And the sample is a subset of that population that is pulled for the purpose of generalizing to the larger population from which they were drawn. And so the purpose of inferential statistics is to make general conclusions about that large population from a small sample of people. Ideally, that sample would have certain characteristics. It would be representative of the population. You wouldn't want to just go and pick the nice people, because then you could only generalize to nice people in the population. You want to select people essentially at random from that population so that you are likely to get a generalizable subset of the population. So now this is this tendency or ability to make an inference from sample data to a population is tremendously important, right? This is a huge distinction because many, many times in this class, we're going to be doing problems that are inferential in nature. And it's easy to think, well, I can see that the mean of this group is bigger than the mean of this group. But that's not what we're going to be doing. What we want to know is the mean difference big enough for us to be able to make a reliable inference to the population. And so that's what we're in the game of. We want to be able to have confidence that the type of generalization we make from a sample is likely to hold in the larger population. So when we talk about populations, we use the term parameter. So populations have parameters. So if we collected the mean of an entire population, which is not very common. So one example of when that would happen is with the census. The census is an attempt to collect parameter data on the population of Americans. When we can't compute parameters, we rely on statistics. And statistics are calculated based on sample data. So you can have a mean of a population, which would be signified by the Greek letter mu, or you can have a mean of a sample, which would be X bar. The mathematics involved in computing a population mean versus a sample mean are identical. But what we do in this class is we try to assess the degree of error that we're going to have when making an inference from a sample to a population, right? And so we have different, we call them different things. We call populations parameters. We use Greek letters to describe them. And we have statistics, which we use traditional Arabic letters to describe. But the calculation of a mean for a population or a sample, no different. There's no mathematical difference. Where the difference comes in is when we try to make an inference, because when we're making an inference, we know that there's a likelihood of some degree of error. And so we are in the business of estimating that error, the error that arises from inferring to a population from a sample. So here we can see that a statistic and a parameter, right? This just depicts it graphically in a different way, that we have the population, we collect data from the population, that data is a parameter. For a sample, it is a subset of that population, a group of people who belong to that population, and ideally who represent that population. Their data is called a statistic. Now, there are a variety of different sources of error that can pop up when doing inferential statistics, right? So we compute the mean of a population parameter and the mean of a sample the same way, but we have to incorporate how likely are we wrong. Think of like the margin of error in a poll, right? When there's a poll, they'll say, they'll estimate who's going to vote for this candidate, who's going to vote for that candidate, and then kind of have like this range of the margin of error, right? Well, that's what we're doing. We're kind of estimating how much error is in our prediction of the population from a sample. So there's a variety of different sources of error. One type is called sampling error. Sampling error represents the discrepancy or amount of error, the amount our guess about the population is off, right? So it's the amount of error between a sample statistic and a population parameter. Basically, it's an error that arises in the data collection process as a result of taking a sample from a population rather than just having all the population data at the beginning. And again, why wouldn't you just have the population data at the beginning? Well, think about that. I would challenge you to try to do a study on schizophrenia with population data. Are you able? Do you have the resources to go out and find every single person in the United States with schizophrenia? Probably not. We don't know the population parameter. We have to infer it from a sample. So sampling error is one reason an estimate of a population parameter is not perfect. But there are other reasons too, right? Errors in our prediction don't just come from sampling error. There are different sources of error. When they're not sampling error, we call them non-sampling error. And so this could be due to using a substandard sampling method, which we'll talk about in a little bit. We could be using measures that have error within them. And we'll talk about that as well. There could also be different behavioral effects. But for now, let's move on and discuss a few of the different sampling techniques that are used that can introduce error into our estimate of the population. So the standard way to establish a representative sample, a sample that can most likely generalize to the population, is to select members of the population at random to be included in our sample. We sample random people. What this means is that each member of that population has an equal chance of being included in the sample. And this is the golden standard, best approach for us to be able to use sample data and make an accurate estimate of the population. So, in other words, if we did not sample at random, this would likely increase our sampling error. So here you can see that we have, a population, which is everyone, and a random sample. The key to a random sample, what randomness means in this case, is that each member has an equal chance of being included in our sample. This ensures that there aren't systemic biases that, like maybe as a researcher, you just had a preference for people who were nice and wanted to participate in your research. They're nice, they want to participate, they call you up and you say, yeah, come on in. Well, then what you're studying is not that whole population. You're studying a subset of that population that wants to be involved in research, right? So you have to be very careful if you're trying to make a generalization to an entire population, particularly if you're not using random sampling. Here we go. We're sampling. Okay, another method is convenient sampling. So this is what I just basically described, right? Whenever we pick people because they're conveniently accessible to us, right? It might be that they live in our neighborhood. It might be that they live in our city. It might be that they want to participate, right? And so it doesn't mean, I'm not in any way insinuating that convenient sampling doesn't allow us to make inferences to a population. I'm just suggesting that they're not as good as random sampling. Certainly, inferences that can be made from a convenient sample to a population are going to be better than no empirical data at all, no inference. But it's certainly not as good as random sampling. Another type of convenient sampling is snowball sampling. So this is, imagine if you were doing a survey and you posted it on Facebook to all of your friends and asked them to post it to all of their friends or Instagram or whatever, Snapchat. And you can see that it's just the people you like, and then those people give it to the people that they like, and then those people give it to the people that they like. It's still not random. People in that population you're trying to generalize to don't have an equal likelihood of being in that sample, and therefore it's not necessarily a representative sample. So here's another example. This is kind of a demonstration of sampling error, right? You can see here we have a population of 1,000 college students with an average age, an average IQ, and a certain proportion of genders in that population. And then we have two samples in the lower left and lower right. So notice that the sample statistics are different from each other, and that both sample statistics are different from the corresponding population, right? So naturally, just by randomly selecting, whatever method was used, there's going to be a difference in the mean that's pulled out of that population. And every time you sample it, you're going to get a slightly different mean, a slightly different breakdown of males to females. And that is sampling error, is the difference between your sample and the actual population parameter. So that error is sampling error. Now, we can never, ever claim that our findings are free of error. But we can do our best through a variety of different methods, but by designing our study appropriately, by using validated, reliable forms of measurement, we can minimize error in our estimation. So now I'm going to transition a little into some terminology this is centrally important. This stuff needs to be part of your vocabulary as we move forward in this class. So the first thing is, what is a construct? Right now, a construct is what we are typically interested in, right? It is a latent thing that we want to measure as psychologists. So for example, we might be interested in measuring love, right? Well, how do you measure love? And there's other examples, right? It's any complex psychological concept, right? It could be motivation, anger, personality, intelligence, attachment, fear. None of these are concrete things. You can't look at love under a microscope, right? But these are called constructs because most of what we care about as psychologists are not physical measurements. They're not time, length, height, weight, pressure, velocity. They're not these things. They're abstract, but that's what psychologists are interested in. And so we have to figure out a way to measure them. And the way we measure them or operationalize them is through variables. So a variable is a measurable definition of a construct. So we might know how love looks, but we can't describe love in inches or pounds or where it starts and where it ends. We have to come up with measures. We've constructed this idea of love, and we have to come up with valid and reliable ways to measure it. So here are a few examples, right? One way, we might do a study where we're assessing love and we look at eye contact or pupil dilation between two people. And that is kind of a partial way, an indicator of love. It's not the whole concept of love, but it is a variable that is related to love. We might ask people, how much do you love each other on a survey? Or we might look at behavior and see, how frequently do partners exchange gifts, or how much money do they spend on each other, right? These are all three of those ways are ways that we could operationalize love that could be a variable. So we might be studying love, but our variable is eye contact or pupil dilation or gift frequency. So some other concepts and definitions, right? So we have data, right? So data is a word that is plural, and it refers to all of the measurements taken on participants in some kind of research study. Now, the singular of data is datum. So you have a datum in a data set. Another vocab word is constant, right? Now, constant is in contrast to a variable. A constant is something that does not change. It is a property or characteristic that stays the same all the time. So the number 8 is a constant. The value pi, 3.1415, right, is a constant. These numbers don't change. They do not vary. A variable is something that takes on different values. It changes. And when we're dealing with psychology, most of the time we're dealing with variables, things that change. No people are identical, right? There might be commonalities between people, but no people are identical. So a variable is like the opposite of a constant. If we're looking at why people become depressed, right? People vary in terms of how depressed they are, right? And what we look at, we try to explain why. Some people are low on depression and some people are high on depression, right? So statistics is about isolating or operationalizing variables about the constructs of interest and explaining why those features vary. So another key distinction here, this needs to really be rapid fire, is the distinction between an independent variable and a dependent variable. So an independent variable is the groups that a participant could be in an experiment, right? Some people get the violent TV group and some people get the non-violent TV group. But really, an independent variable, you can think of it as the predictor variable. It doesn't have to be groups. It's the thing that we think is going to predict the outcome of interest, the construct that we're interested in. The dependent variable represents the variable, the outcome variable, what we're interested in. And we want to see if an independent variable can explain, predict, or cause change in a dependent variable. So one way to keep this straight, there's a couple, simple ways that you can think about this, but one is that the dependent variable depends on the independent variable. Another way is you can use it in a sentence. If you say, the researcher was interested in the effect of blank on blank. The first blank is independent variable, and the second blank is dependent variable. So we're going to be using these terms, what's the independent variable, what's the dependent variable, every single class. Another distinction is the distinction between an experiment and an observational study. So in an experiment, a researcher manipulates or controls an independent variable. Manipulate's actually the more appropriate word here, right? So the researcher determines who gets what. When a researcher does that, particularly whenever people are randomly assigned to one group or another group, and then the effect of that random assignment on the dependent variable is studied, right? This is an experiment. That is a classic gold standard experiment. Experiments are special in that because the researcher manipulates the independent variable and examines the change the independent variable has on a dependent variable, causal inferences can be made. You can say that because everything else is the same except what the experimenter manipulated. That the cause of the change in the dependent variable is due to that manipulation. Now, alternatively, there are observational studies. This is when a researcher doesn't manipulate or control an independent variable, but simply observes the values as they naturally exist, right? Maybe you're observing people doing something, right? Another word for this is a correlational study, where we're seeing how this variable and this variable relate to each other, right? Rather than trying to fix one so that some people get one thing and other people get another thing. Now, one thing in an experiment that is absolutely crucial is we want to make sure if, say we have a study where we're doing violent TV versus non-violent TV on how violent people are in their daily life. Well, we want to make sure that we're not biased in who gets what, right? We want to make sure that we don't put all of the peaceful people in the control group or all the peaceful people in the violent TV group. We have to be as unbiased as possible. And the best way to eliminate that bias is using randomness, right? We want to randomly distribute people to assign them into each group. So what we're doing is we're making sure that each person who is randomly sampled from a population into our study is then randomly assigned to a condition in the experiment. So we've talked about simple random sampling. We've talked about random assignment. So just to be clear, random sampling is when we select people for inclusion in our sample at random. And the purpose of this is to promote generalizability to the population from the sample data. Random assignment is when we randomly determine which participants in our sample will receive a particular level of the independent variable. What group, what condition are they in? Placebo or experimental group or treatment group? So the key here is that both of these rely on randomness, meaning that all people have an equal likelihood of being selected or being assigned to a particular group. And the idea behind this is to make it so that our bias is not introduced, and we can have more confidence in that inference, or in the confidence in the inference or the effect of the independent variable on the DV. So another distinction here is an extraneous variable and a confounding variable. So these are things that we don't like to deal with, right? So if we aren't prepared, we're going to encounter these. Sometimes even if we are prepared. But an extraneous variable is any variable related to the outcome that is not of interest to the researcher. So in a confounding variable, it's the same as a extraneous variable, except it affects both the independent variable and the dependent variable. So we don't like to deal with confounding and extraneous variables. They mar our ability to make an inference, right? And beyond just being able to make an inference, they mar our ability to know that the effect, particularly for confounding variables, that the effect of the independent variable on the dependent variable is due to the manipulation and not the confound. So we want to get rid of these as we plan some kind of study. Well, that wraps up this second part of the second lecture. and I hope it was helpful for you. If it was, don't forget to like the video and subscribe. If you hit the notification bell, you'll get updates on every lecture I post as I post it. Okay, thank you. Have a good day. I'll see you in the next part.